In this video, we are going to be looking at the statistics portion of the year 2023 A-Level H2 Math paper. And we are going to be looking at question number 5, which is the first question in the statistics portion of this paper. It is a probability question. We are looking at a child's toy with 36 slots. They are numbered from 1 to 36. And when a ball is dropped into this toy, there is equal chances of the ball dropping into any of these 36 slots. We are looking at 4 events A, B, C, D. Let us first try to quote the probability of each of these events. So for example, for the probability of A, we are talking about A having a score which is going to be the number that the ball is going to be falling into. So for A, it is going to be recording scores that are odd numbers. So 1, 3, 5, and so on. There will be 18 of them out of these 36 slots. So it will be 18 over 36. This is half. We can also look at the probability of B, which are consisting of all the evens score. So there will also be 18 of them. So this is going to be 18 over 36. This is also equal to half. And then probability of C, which will be the scores that are of multiples. There are multiples of 3. So for the probability of C, we can try to list down some of the terms, not some. We should list down all of the terms where it consists of multiples of 3s. So it is going to be 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, and then 36. There are 12 of them. So this is going to be 12 over 36. This is equal to 1 over 3. And D is when the score is a multiple of 6. So to list down all those that are of multiples of 6, they will be 6, 12, 18, 24, 30, 36. And there are 6 of them. So this is going to be 6 over 36. This is 1 over 6. And now we are ready to do A part 1. A part 1, we want to state which pairs of the events here, they are mutually exclusive, so they cannot happen at the same time. So I think the most obvious one will be A, B, because this will be odd numbers, this will be even numbers, so they definitely cannot be existing at the same time. So we will say A and B, they are mutually exclusive. And let's try to also analyze, let's say, A and C. A and C are not mutually exclusive because A will be odd numbers, and we are seeing some odd numbers here. Okay, so it is not going to be A and C. How about A and D? D are all consisting of even numbers. So odd numbers, even numbers, they cannot exist at the same time. So another possible pair will be A and D. How about B and C? B and C, B is even numbers, and we are seeing some even numbers here, so they are not mutually exclusive. B is even numbers, and for D, if I were to analyze B and D, all these are even numbers, so they are definitely not mutually exclusive also. So I guess these are the only 2 pairs that are mutually exclusive. So A and B, A and D, they are mutually exclusive. Part 2. Part 2, we want to show that A and C are independent events. So to show 2 events are independent, I'm going to make use of the fact that if we can actually show that probability of an event X intersect event Y is equal to probability of event X multiplied by the probability of event Y, then we can say that X and Y, they are independent. So I'm going to make use of this to try to show that A and C are independent. Let's try to first quote the probability of A and C. So A are odd numbers, C are numbers that are like this. So for odd numbers, there are also here will be 1, 2, 3, 4, 5, 6. So this is going to be 6 over 36. This is 1 over 6. And let's try to take the probability of A multiplied by the probability of C to check whether numerically they share the same value. So probability of A is going to be equal to 1 over 2 probability of C, this is equal to 1 over 3. And this is equal to 1 over 6, which is equal to probability of A intersect C. So this, I can then say that A and C, they are independent. Okay, and we want to state another pair of independent events. So the thing is, when two events are mutually exclusive, they cannot be independent because A and B will be equal to 0. Okay, and A and D will also be equal to 0. Individually, A has a number, so it is A and D, they both have numbers that are non-zero, so it is impossible for AB, AD to be mutually exclusive. So we are going to look at alternatives. Okay, so let's just think about what are the alternatives that we have first. So we are rejecting this already. A and C, we have already done our analysis. So the next thing that we can try to analyze will be, let's say B and C. We can analyze B and C. Then another one will be B and D. Okay, so let's analyze these two and let's see which of them, or maybe even both of them, are going to be independent. So let's try BC. So for BC, we are going to analyze the probability of B intersect C first. B will be scores that are even numbers. So let us count the even numbers. We have 1, 2, 3, 4, 5, 6. So this is also going to be 6 over 36. This is equal to 1 over 6. Let's try to check the probability of B multiplied by the probability of C. The probability of B is equal to 1 over 2. The probability of C is 1 over 3. This is again 1 over 6. So we can, based on this, we can say that B and C are independent. So this tells me that therefore B and C, they are independent. In fact, this should be the other pair of independent events that the question is asking for. But maybe let's just do a quick check, okay? Just in case B and D, right, they are also going to be independent of each other. So B will be even numbers, D will be the numbers that are here. And all these numbers are even, which means that if I were to be finding out the probability of B and D, this is going to be 6 over 36. It is 1 over 6 because it is all these 6 numbers. They are also overlapping with this B. And if I were to try to find the probability of B multiplied by the probability of D, it is going to be probability of B, this is going to be equal to 1 over 2. Probability of D, this is equal to 1 over 6. This is going to be equal to 1 over 12, and they are not equal to each other. So we know that B and D, they are not going to be independent. Okay, so this is for part A. Let us proceed to take a look at part B. So in part B of the question, we are going to be analyzing another situation where the slot that is labeled 36 is no longer available for the ball to be dropping in. So maybe let's try to recalculate this probability of events A, B, C, and D. So now 36 is not available anymore, which means that for probability of A, which are all the odd numbers, it will be from 1 all the way until 35. There are actually still 18 of them, so it's going to be 18 over 36 is going to be equal to this. But for even numbers, because 36 is no longer available, so we will have just 17 instead of 18 left. So my answer for this probability of B is going to be this over 35. In fact, I should be changing this also, because the denominator should be left with just 35. So let me change this. Probability of A will be 18 over 35. So probability of B will be 17 over 35. As for the probability of C, 36 is no longer available. So we will have 1 less here. So this is going to be 11. Then here, it will be over 35. Okay, so we will have this. Isn't it convenient that I can just erase from here? So for D, again, 36 is not available anymore. So we will have 1 less than 6. And here is going to be 5, which means that we will have a 5 over 35. This is equal to 1 over 7. And now let's start with B part 1. We want to state which pair of the 4 events are now mutually exclusive. So again, let's try to do our analysis. A and B, these are odd numbers. These are even numbers. They are definitely going to be mutually exclusive. They cannot happen at the same time. So we know A and B are going to be mutually exclusive. Let's try to think about A, C. So A are odd numbers, C consists of odd numbers also, so they can happen at the same time for certain cases. So not A, C. And for A, D, these are odd numbers. D are all still even numbers. So we know that A and D, they're also going to be mutually exclusive. How about B, C? B are even numbers, and we see some even numbers here, so B, C are not mutually exclusive. And these are all even numbers, so it will definitely overlap big time with B. So it is still going to be the same. A and B, A and D are mutually exclusive. Okay, so this is part 1. Part 2, determine whether A and C, they are now independent. So we are going to use the same strategy. We are going to try to find the probability of A and C first. So A are odd numbers. For C, we are looking at 1, 2, 3, 4, 5, 6. So it will be 6 over 35. And we will try to check this against probability of A multiplied by the probability of C. Probability of A will be now 18 over 35. And the probability of C, this is going to be equal to 11 over 35. This is equal to 198 over 1225, which is not the same as probability of A intersect C. So in this case, we are going to say that A and C, they are no longer independent. Okay, this is for question number 5, our first statistics question that require a little bit more observation and a bit of trial and testing as compared to normal, but it is still okay. Let's move on to the next question. Let's take a look at question number 6. Okay, question number 6. We are looking at May holding on to 12 counters, where these 12 counters are going to be chosen from R red counters and B blue counters. And in part A, we are supposed to show that 9R plus 5 is equal to 4B when we are given this piece of information. The probability that May is going to be getting 4 red counters out of these 12 counters that she's holding will be the same as the probability that she's going to be getting 3 red counters. So let's try to match the two probabilities together, and through that, we will most likely be able to show that 9R plus 5 is equal to 4B. So let's try to calculate for the probability that May is going to be getting 3 red counters out of the 12 counters that she has, which means that out of the R number of red counters, we are going to be, May is going to be choosing 3, and out of the blue counters, because total May will be having 12, so 12 minus 3, that will be 9. So we are going to be getting 9 blue counters, and we are looking at the probability. So let me divide by, out of R plus B number of counters, we are going to be choosing 12 counters. Okay, this is going to be equal to the probability that May is going to be obtaining 4 red counters. So that will be, of all the red counters, we will choose 4. Of all the blue counters, we will now choose 8. So 4 plus 8 is equal to 12. This is going to be divided by all the possible outcome, which is going to be out of R plus B number of counters, we are going to choose 12. So based on this, let's try to see whether we can simplify it to get 9R plus B is equal to 4B. So the denominator can be cancelled. We're going to be left with just the numerator. For R choose 3, we can actually refer to our formula sheet. It will give us a way to rewrite R choose 3 in terms of all the factorial notations. And R choose 3 will be R factorial divided by 3 factorial multiplied by R minus 3 factorial. The same goes for B choose 9. B choose 9 will be B factorial divided by 9 factorial multiplied by B minus 9 factorial. R choose 4, it will be R factorial divided by 4 factorial, R minus 4 factorial. B choose 8, that will be b factorial divided by 8 factorial multiplied by b minus 8 factorial. So the numerators can be cancelled. R factorial will disappear. B factorial will also disappear. Let's just do a quick cross multiplication maybe, or we can just simply match the denominator to be equal to each other. So if I were to cross multiply, it is going to be 4 factorial, r minus 4 factorial. Then we have an 8 factorial, b minus 8 factorial is equal to 3 factorial, r minus 3 factorial, 9 factorial, then b minus 9 factorial. And when it comes to simplifying all these factorial notations, if there are those that are sort of like comparable or related to each other, I'll usually try to break down the bigger valued term. For example, between 4 factorial and 3 factorial, 4 factorial is bigger, so I'm going to rewrite 4 factorial as 4 times of 3 factorial. So later we can cancel away the 3 factorial. And between r minus 4 factorial and r minus 3 factorial, this is bigger. So let me just keep this as it is. And I'm going to rewrite this. So 3 factorial, I'm going to just keep it. This, I will rewrite it as r minus 3 multiplied by r minus 4 factorial. Between 8 factorial and 9 factorial is bigger. So 8 factorial, I will just leave it as it is. As for 9 factorial, I'm going to write it as 9 multiplied by 8 factorial. Then between these two, this is bigger, so I'm going to rewrite this as b minus 8 multiplied by b minus 9 factorial. So this, I'll just leave it as it is. We have a b minus 9 factorial. So now let's try to cancel away terms that are the same. So this 3 factorial, we'll be cancelling them away. r minus 4 factorial, we will also be cancelling them away. 8 factorial disappear, and we will have a b minus 9 factorial to disappear also, which means that on the left, we are going to be left with 4 times of b minus 8. This is going to be equal to, on the right, we have a 9 times of r minus 3. So 9 of r minus 3. And if you were to just rearrange this, you will be getting a 9r plus 5 is equal to 4b. Okay, and this is what the question is requiring us to show. So this, done. And in part B, we are going to try to derive an equation that is similar to A with a bit less instruction, but it is almost the same process, except that the information that is given to us is such that the probability of May getting 3 red counters is 5/3 times of the probability that she will be getting 2 red counters. So we'll do the same thing. For May to be getting 3 red counters, it will be R choose 3, then B choose 9, divided by R plus B choose 12. And for May to be getting 2 red counters, this probability, according to the question, is 5/3 of the probability that May will be getting 2 red counters. That will be R choose 2, then B choose 10, divided by R plus B to choose 12. Okay, so the denominator can be cancelled, so this will disappear. Let us do a quick cross multiplication again. So this, it will be 3 times of R choose 3, B choose 9 is equal to 5 times of R choose 2, then B choose 10. Let's try to expand it just like how we have done it here. So it's going to be 3 times of, this will be R factorial over 3 factorial, R minus 3 factorial. This is going to be B factorial over 9 factorial, then R minus 9 factorial. This is 5 times of, this will be a 5 factorial divided by 2 factorial, R minus 2 factorial. This is B factorial over 10 factorial, then B minus 2 factorial. Sorry, B minus 10 factorial. Yeah, 10. So again, this, just like what we have experienced previously, they can be cancelled. We're going to do another round of cross multiplication. So this is going to be 3 times of 2 factorial then r minus 2 factorial, then 10 factorial, then b minus 10 factorial. It's going to be 5 times of 3 factorial, then r minus 3 factorial, 9 factorial, r minus 9 factorial. Let's once again try to rewrite those comparable but the bigger version. The bigger one, I'm going to just break it down just like what we have done here. So 3, I'll just let it be for now. 2 factorial, I'm going to compare it to this 3 factorial. So 2 factorial, I'm going to just keep it as it is. As for this, I'm going to rewrite 3 factorial as 3 times of 2 factorial. Okay, then we have a r minus 2 factorial, r minus 3 factorial. This is bigger. I'm going to write this as r minus 2 multiplied by r minus 3 factorial. So here we have a r minus 3 factorial. 10 factorial, 9 factorial. I'm going to rewrite 10 as 10 multiplied by 9 factorial. And this, I'll just write it as 9 factorial. And finally, b minus 10 factorial, b minus 9 factorial. This is bigger. So this, I'm going to just let it be as it is. This, I'm going to write it as r minus 9 multiplied by r minus 10 factorial. Let's do the cancellation. So when we want to try to do the cancellation, oops, I've made a mistake. This should be a b minus 9, which means that here it should be a b minus 9. So here it should be a b minus 9 and b minus 10 factorial. Okay, so based on this, let's try to do some cancellations, okay? So we are seeing the 2 factorial being cancelled. In fact, this 3 and this 3, they can also be cancelled. Then we are going to cancel r minus 3 factorial. And then this 9 factorial, we are also going to be cancelling them. Then b minus 10 factorial, we will also cancel. Which means that on the left-hand side, we are going to be left with a 10 times of r minus 2. Let me write it here. Maybe here. So on the left-hand side, we will have a 10 multiplied by r minus 2. And on the right-hand side, we are going to be left with 5 multiplied by b minus 9. So 5 times of b minus 9. Shifting everything over to one side, we have a 2r plus 5. This is equal to b. This will now form for me equation number 2. And I'm going to try to solve it against equation number 1 as a pair of simultaneous equation. So you can bring all the r's and b over to one side, then solve it using the GC. So, solving using our GC, we will get the values of r and b. R is going to be equal to 15 and b is going to be equal to 35. So with this, we are now going to try to calculate for the probability that just one of the 12 counters removed is red. So from here, the very last part, the required probability that we are going to be working on will be out of the 15 red, we are going to be choosing 1 because this is the criteria that is mentioned to us by the question. We want to have just one of the 12 red counters removed is red. So red counters, choose 1. And for the blue counters, we will choose 11. Divided by the total will be 15 plus 35. So 15 plus 35, we're going to choose 12. Pressing this into the calculator, the probability here is 0.0516. Okay, this is for question number 6. Tedious. Let's continue. Let's take a look at the next question. Okay, let's move on to question number 7, which is a product moment correlation coefficient question. We're given this set of data and we want to try to analyze whether they are going to be fitting to the two models that are proposed. One is y is in terms of x, the other one is e to the power of y in terms of x. So we are going to impart a over here. We are going to try to determine the value of the product moment correlation coefficient of this, and then to try to find the product moment correlation coefficient of this. So for A, part 1, let us try to use our graphing calculator to find the product moment correlation coefficient by planting these two lists into our calculator. Stats, edit. I've already done it So x, I've already planted it into L1, and y, I've planted it into L2. Let's base on these two lists to calculate the product moment correlation coefficient. I'm going to use 8, although 4 is totally fine. Like if I were to use 8, x list, I'm going to go for x values, which is in L1. Y list, I'm going to go for the y values, which is in L2. Calculating for this using our calculator, this is going to be equal to, okay, this is the product moment correlation coefficient. It is 0.9281 to 4 decimal places according to what the question requires. And in part 2, we are going to try to also calculate the product moment correlation coefficient. This time in part 2, we are going to use the same data, and we're going to calculate a product moment correlation between x and e to the power of y, which is going to be simulating this equation instead. So we need an e to the power of y list, and to do that, let me press stats. And in edit, let me go for L3 to be one that represents e to the power of y. So in L3, let me press second ln, which gives me this e to the power of. It is going to be e to the power of y, so it is in L2. So with this, enter, so this will be all the e to the power of y values. Pressing stats again using my choice of 8 instead of 4. We are going to try to alter this. X list, I'll let it be x, which is in L1. Y list, I'll let it be e to the power of y, which is in L3. So here, let me press in L3. Let's do a calculation, and let's see what we are going to be getting. Okay, so the product moment correlation for this is 0.9697. Okay, so we have this product moment correlation coefficient. In part B, we want to explain which of the model is going to be a better fit, and we want to find the equation of this particular model. I mean, it is pretty obvious. Okay, between these two product moment correlation coefficient that we have, we know that this has a magnitude that is going to be closer to 1. So therefore, in part B, we will say based on this, e to the power of y is equal to cx plus d is the better model, is a better fit. And this is because modulus of r is closer to 1. Okay, modulus of r of this model is closer to 1. So what is the equation of this model? So for the equation of this model, let's look at our calculator again. We're going to use these numbers. So we have e to the power of y is equal to this. I'm going to go for this. 376x plus d. D is going to be minus 188. Here will be minus 1881. Okay. So, oops, I should write it as minus 1880. Okay, if I were to go for 3 significant figures, yep, this should be the better version. So this is for B, and for C, the question requires us to do a prediction. For C, we are going to try to use this equation to estimate the mobile phone subscription in the year 2024. And we need to try to see it from the X perspective. So 2004, X is 4. 2006, this is 6. 2008, this is 8. Which means that for 2024, we are going to be letting x be equal to 24, which means that e to the power of y is going to be equal to this. But this time, I should use at least 5 SF. So let me just display what we have here again. Using 5 SF, we are talking about 375.62 multiplied by 24 minus this, it will be 1881.5. And calculating for y by doing a ln on this will be 8.87. So this will be our estimation of the number of mobile phone subscription. And do we think this is reliable? This is not reliable, because if I were to look at the data that is given to me, we are looking at x to be between 4 to 18, but we are now trying to do an extrapolation. So I'll say something that is like this: as x is equal to 24 is not within the data range. Within the data range. And this data range, according to what I can see in the question, it is going to be from 4 all the way until 18. So therefore, this estimate is going to be unreliable. Okay, this is for question number 7. Let's move on. Let's take a look at question number 8. Okay, let's take a look at question number 8 over here. It is a hypothesis testing question. And in part A of the question, we are supposed to state the null and alternative hypothesis. So the first thing that I'm going to do is I am going to define mu, which is going to be the mean weight of a bag of the granulated sugar. So for the null hypothesis, we are talking about mu according to the question to be 1. And as for the alternative hypothesis, we are talking about mu to be not equal to 1. And this is for part 1 of the question. In part 2 of the question, it is given to us that the production manager decides to take the first bag of sugar produced each morning and the first bag of sugar produced each afternoon in a 5-day working week to form a sample of 10 bags. We want to give 2 reasons why the production manager, the sample that is from this production manager, is not suitable for a z-test. Z-test will require the test statistics to be following a normal distribution. And for the situation that is given to us, we are not very sure whether the weight of the sugars are actually already following a normal distribution. So the ideal case will be for us to be applying the central limit theorem to do an approximation. But too bad, the production manager is only getting 10 samples of the bags. So the sample size is too small for central limit theorem to take place. So this is the first reason that I'm going to be giving. The second reason will be the way that this production manager is collecting the sample, collecting the data. Because the production manager is just collecting the data once in the morning and then once in the afternoon. I think the collection of data can be even more spread out throughout the day. So the way that is the collection of data is carried out, I think it may not be a fair representation of how the entire production is going to be taking place. Okay, this is my second reason. Let's move on to part B. Part B, we are looking at now the company using a different machine and the information is given to us as that. In part 1, we are going to try to state the hypothesis and to find the critical region for this test. So for this part 1, H0 will be mu. In this case, it is now going to be 2 kg. So mu is going to be equal to 2. And as for H1, H1 will be such that, according to what the question is saying, we are trying to test whether the average mass of the sugar is in fact less than 2. So this is going to be a left tail test. This is less than 2. And we want to try to find the critical region for this test. So we want to build the bell curve that represents this hypothesis test. So for the bell curve, since we don't know whether the weight of the bags of sugars are following normal distribution, so we are going to be applying the central limit theorem. And to build that test statistics, we need the population mean, which we have, it is 2. We need the population variance, which we don't have, so we should calculate it by doing an unbiased estimate based on the sample that is given. And of course, we need the sample size. In this case, the sample size is 40. So let's try to calculate an unbiased estimate to the population variance first. And this is going to be 1 over n minus 1, summation of x squared minus summation x, this whole thing square, divided by n. This will be 1 over n is 40, 40 minus 1. And here we have a 155.6746. This is given to us by the question. This will be 78.88. So square, this is going to be divided by 40. So this is equal to 0.00316. And based on this, we can now code the test statistics for our z-test. And to code this test statistics, we are looking at n to be equal to 40. And this is actually large enough for us to apply the central limit theorem. So x bar will now follow a normal distribution with a mean of 2 and a variance of 0.00316. Population variance, the unbiased estimate version of it, divided by the sample size. This is by the central limit theorem. as an approximated distribution. So based on this, we can try to imagine the critical region on the bell curve, where this bell curve is going to be following this normal distribution. The center of this bell curve here, this is equal to 2. And we are talking about a left tail test, which means that all the way on the left-hand side here, this region is going to be the critical region. According to the question, we are trying to carry out the hypothesis test at 2.5% level of significance, which means that this is going to be 0.025. Okay, 2.5% level of significance. So what we need is this particular value with this as our normal distribution. We can use our calculator to find this value, and pressing into our calculator to find this value, we will get this value from the calculator to be 1.9826. So therefore, based on this, we can describe the critical region. The critical region will be when x bar is going to be less than or equal to this 1.98. Okay, this is for part 1. And for part 2, state the conclusion of the test in the context of this question. And since we already have the critical region, what we need to do is to just check whether the sample mean is within the critical region or not within the critical region. And we can easily check that because according to what that is given to us by the question, n is equal to 40 and summation of x is 78.88, which means that we can find x bar, the sample mean. This sample mean will be 78.88 divided by 40. This is 0.197. And since x bar here, which is 0.197, is less than 1.98, so it is within the critical region. Let me write it down. At 2.5% level of significance. Okay, this is for question number 8. Okay, nice. Let's continue. Let's take a look at question number 9. Let's now take a look at question number 9, where we are going to be looking at the length of different planks, regular planks and long planks. And according to the question, the length of long planks are going to follow normal distribution. So I am going to let x be the length of the long planks that the question is asking for. So x will follow, according to the information that is given to us by the question, it will follow a normal distribution with a mean of 1.82 and a variance of 0.2 square. And in part A, we want to find the probability that the length of a randomly chosen long plank is less than 1.79. This is very easy. It is calculating for the probability that x is less than 1.79. We just need to press this into the calculator, and this will give me a 0.440 for part A. Part B, we want to find the probability that the total length of 8 randomly chosen long planks is greater than 14.5. So for part B, we are looking at the total length of 8 randomly chosen long planks. So we are looking at x1 plus x2 plus all the way until x8. So in order for me to find the probability, let's try to construct a new normal distribution that represents this. So to do that, I will first need to find the expectation of this, which is going to be 8 times the expectation of expectation of x. So it's going to be 8 times of 1.82. This is equal to 14.56. And we also want to find the variance of x1 plus x2 all the way until x8. This is going to be 8 times the variance of x. So it will be 8 times of 0.2 square. This is equal to 0.32. So x1 plus x2 plus all the way until x8 will follow a normal distribution, where the mean is going to be 14.56 and the variance is 0.32. We are basically doing a linear combination of normal distribution. That is why we know that the combined distribution will also follow a normal distribution. And our aim is to try to find the probability that the total length is going to be more than 14.5. And this, pressing into the calculator, we are going to get a 0.542. Okay, we're going to move on to C, and when C, we are looking at regular planks. Okay, so we are looking at regular planks, and I'm going to let y be the length to represent I'll let y be representing the length of a regular plank, and it follows a normal distribution that is given to us by the question. And in part C, this person is going to be buying 120 regular planks. We want to calculate the expected number of these planks that are going to be longer than 1.25. So we are looking at the average number of the planks that are inside this 120 planks that are going to be longer than 1.25. So I think what I'm going to do is I am going to calculate for the probability when one of the regular planks has a length that is more than 1.25 first. And this, pressing to the calculator, is 0.46017. And I'm going to try to apply this to the 120 regular planks that this person bought. So I'm going to introduce binomial distribution in my calculation. I am going to let W be the number of regular planks that are going to be longer than this, that are longer than 1.25 meters out of the 120 planks, out of 120 regular planks, which means that W here will follow a binomial distribution. Out of 120, we are looking at planks that are more than 1.25, and the probability is 0.46017. So what the question wants is the expectation of W, which is going to be n times P. So it's going to be 120 multiplied by 0.46017. This is going to be equal to 55.2. Okay, this is for part C. Let's move on. Let's take a look at part D. And for part D, we are going to try find the probability that the total length of 10 randomly chosen long planks differ by less than 0.6 meters from the total length of 16 randomly chosen regular planks. So we are looking at the total length of 10 long planks. So it is going to be x1 plus x2 plus all the way until x10. We are going to be comparing. We are going to find the difference between this and the total length of 16 randomly chosen regular planks. So that will be y1 plus y2 plus all the way until y16. We are going to be looking at their difference. And in order for me to calculate the probability such that their absolute difference or they differ by less than 0.65, we are going to try to form a new normal distribution based on this. Okay, so to do that, we will first find the expectation of this, which is going to be 10 times the expectation of x minus away 16 times the expectation of y. So it's going to be 10 times of 1.82 minus away 16 times of 1.22. This is equal to minus 1.32. We also want to find the variance in order for us to form the normal distribution for this. So the variance of x1 plus x2 all the way until x10 minus away y1 plus y2 all the way until y16. This is going to be 10 times the variance of x minus will become plus 16 times the variance of y. And this is going to be 10 times of 0.2 square plus 16 times of 0.3 square. This is equal to 1.84. So based on this, x1 plus x2 plus all the way until x10 minus y1 plus y2 all the way until y16, this will follow a normal distribution with a mean of minus 1.32 and a variance of 1.84. And we want to find the probability that, according to what the question says, we want to find the probability that they are going to differ from each other by less than 0.65. So we are going to try to find the probability that they differ. So we don't know which one is supposed to be bigger. So we want to add in a modulus of x1 plus x2 all the way until x10 minus y1 plus y2 all the way until y16. This must be less than 0.65. Okay, so this is the probability that we are supposed to be calculating. And in order for us to be able to press the calculator, we are going to try to remove the modulus by rewriting this into this to be between negative 0.65 all the way until x10 minus y1 all the way until y16 between negative 0.65 and 0.65. So from here, we can press into the calculator using this as the normal distribution. My answer here is going to be 0.237. Okay, so this is for part D. And we have one last portion of this question to try to deal with. So let me erase this first. So in this last part, part E, not last part, the second last part, but this is the last portion of this question. We are going to be looking at this company trying to get some shorter planks. They are called short planks. So the shorter planks, these short planks are going to be obtained by either cutting the long planks into 3 exactly equal lengths or cutting the regular planks into 2 exactly equal lengths. So we want to find the probability that the length of the short planks that are derived from the long planks is greater than the length of the short planks that are derived from the regular planks, assuming that there's no wastage. There's no wastage. So for part E, what we are going to first do is we are going to look at the length of the short planks that are derived from the long planks. And I'm going to name the length of these short planks as SL. So it is the length of short planks that are derived from the long planks. So I'll let SL be the length of a short plank that is derived from a long plank. Okay, so this SL is going to be equal to 1 over 3 times of x, because x is going to be divided by 3 times. And what I'm going to do is I'm going to come out with the distribution for SL by finding first the expectation of this. So it's going to be the expectation of this. It is going to be 1 over 3 expectation of x. So it's going to be 1 over 3 multiplied by 1.82. And this is equal to 0.60667. Okay, so we have this. And we want to look at also the variance of SL, which is going to be the variance of 1 over 3x. And this will be 1 over 3 square variance of x. So it will be 1 over 3 square multiplied by 0.2 square. And this is equal to 0.00444444. Okay, so based on this, SL is going to follow a normal distribution because it is a linear combination of another normal distribution. So it will be a normal distribution with a mean of 0.60667 and a variance of 0.00444444. We are going to do likewise for the length of the short planks that are derived from the regular planks. So I am going to let SR be the length of a short plank that is derived from a regular plank. And according to what the question says, a regular plank will be divided into half. Okay, so SR will be represented by half of y. This is the length of a regular plank. So we are going to try to do the same thing to find the expectation of this, which is going to be half times the expectation of y. So it's going to be half times of 1.22. This is equal to 0.61. And we want to find the variance of SR, which is going to be the variance of half y. And this will be half square variance of y. And this is going to be half square multiplied by 0.3 square. This is going to be equal to 0.0225. So this will give me the normal distribution for the length of the short plank that are derived from the regular planks. So this is going to follow a normal distribution with a mean of this and a variance of 0.0225. And what we want to do is to calculate for the probability that the length of this is going to be greater than the length of this. So we are looking at SL minus SR. So to look at SL minus SR, let's try to form another normal distribution for this. So it's going to be the expectation of this, which is going to be the expectation of SL minus away the expectation of SR. Expectation of SL is 0.600667 minus away 0.61, and this is equal to negative 0.00333333. And then we want to find the variance of SL minus SR. This is going to be the variance of SL minus will become plus the variance of SR. So this is going to be this 0.004444 plus variance of SR, see, it's going to be 0.0225, and this is 0.026944. So based on this, SL minus SR will follow another normal distribution with a mean of 0.00333333 and a variance of 0.026944. And what the question is asking us for is to calculate for the probability that SL is bigger than SR. And this can be calculated by going for SL minus SR is bigger than 0. And we have a normal distribution that represents this. So we can now press into the calculator. And from my calculator, the probability is 0.492. This is for part E. We have one last part, which is a 1-mark question. And it says that without doing any detailed calculations, we are supposed to explain how the answer that is in part E will change if now that cutting the plank will actually cause a small amount of wastage. I'm not exactly sure how the answer should be like, so I'm going to just reply to this based on my own logical thinking. So what I'm thinking of is, because for the long plank, it is going to be divided into 3 parts. But for the regular planks, it is going to be divided into just 2 parts. So we need to go for more cuts to the long planks to get the short planks. As compared to the regular planks, we just need 1 cut. Okay, long planks, we need 2 cuts to get 3 equal parts, right? So, and because every cut there will be some wastage, which means that for the long planks, we will be expecting more wastage than the regular planks, both deriving the short planks. And that is why now for the length of the short planks that are derived from the long planks, which has now more wastage that is happening, I'll be expecting that the length of the short planks derived from the long planks will be shorter than usual as compared to this. And that is also why when I try to calculate for the probability that the length of the short planks derived from the long planks to be bigger than the length of the short planks derived from the regular planks, this time, because generally it is shorter, the probability of this happening should also be smaller than this. Okay, that is my take for the last part, F. Okay, let me move on to the last question of this paper, question number 10. Okay, we are going to look at question number 10, and for part 1A, part 1, we are supposed to state 2 assumptions such that the number of 40 ornaments in a day can be well modeled by a binomial distribution. So for me, I will assume that the probability of any ornament being 40 is going to be the same, so that I can apply binomial distribution. And also for one ornament to be 40, it is going to be independent to another or any other ornaments that are going to be 40. So this will be my 2 assumptions. And assuming that the number of 40 ornaments produced each day is really going to be following a binomial distribution, I'm going to let X be the number of 40 ornaments that are going to be produced in a day. And according to the question, this X here follows a binomial distribution. So let me quote it down here. 50 produced in a day, and the probability of an ornament being faulty is 0.04. That is what I interpreted from this binomial distribution. So in part 2, we want to show that the numerical value of the mean and the variance of this distribution is going to differ by 0.08. So the mean will be expectation of x and the variance will be the variance of x. So what the question wants is for the numerical difference between these two. So it is going to be the modulus of expectation of x minus away the variance of x. And this is going to be, the expectation will be n times p. So it's going to be 50 multiplied by 0.04 minus away variance is going to be n times p times 1 minus p. So that will be 50 times 0.04 times 1 minus 0.04. Pressing this into the calculator, this is equal to 0.08. Okay, this is what we are supposed to be showing for part 2. And for part 3, we are supposed to find the probability that there are no more than 2 faulty ornaments that are going to be produced in a randomly chosen day. So we are trying to find the probability that x is going to be less than or equal to 2. We can press this directly into the calculator and that will give me a 0.677. This is part 3. And for part 4, we want to find the probability that there are no more than 2 faulty ornaments that are produced on at least 3 days in a randomly chosen 5-day working week. So we are looking at another binomial distribution. And I'm going to let, for example, y be the number of days with no more than 2 faulty ornaments that are produced. Faulty ornaments that are going to be produced out of this 5-day work week, out of 5 days. Okay, it should be produced, maybe I should add in, that is produced in a day, out of the 5 days. So based on this, we know that y will follow another binomial distribution where it is going to be out of 5 days. The probability of success for the binomial distribution, the probability here is the probability that one day has no more than 2 faulty ornaments that are produced, which is actually this probability. So this is going to go into here. And of course, we have to use at least 5 significant figures. So writing down this here, but in 5 significant figures, it will be 0.67671. And our aim is to try to find the probability that there are at least 3 of such days. And in order for us to press into our calculator, I will try to rewrite this as 1 minus probability that y is less than or equal to 2, because we want 3, 4, and 5. So I will minus away 0, 1, and 2. So this, based on our calculator, is 0.805. This is for part 4. And part 5. We want to find the probability that there are no more than 10 faulty items that are produced in a randomly chosen 5-day work week. And according to what we are seeing here, we know that one day, 50 ornaments are going to be produced. So in 5 days, we will be getting 50 times 5 ornaments that are going to be produced. So out of these 50 times 5 ornaments that are going to be produced, we want to make sure that there are no more than 10 faulty items that are going to be produced, 10 faulty ornaments that are produced. So I am going to come up with another random variable. I'm going to let it be w. I'll let w be the number of faulty ornaments that are going to be produced in the 5 days, not 50, 5 days. Okay, it's just 5 days. So the total number of ornaments that are going to be produced, like what we have just discussed, right? It is going to be 5 days, and 1 day, 50 are going to be produced. So in 5 days, 5 times 50 are going to be produced. And the probability of an ornament being faulty, since we have already had this assumption, so the probability is going to remain the same, which gives us W to be a binomial distribution. Here it will be 250, 0.04. And according to the question, we are looking for the probability that W is supposed to be less than or equal to 10. So we can press this into the calculator also. This is equal to 0.583. Okay, this is for part A. Let's move on. Let's take a look at part B. Okay, let's take a look at part B. And the first thing that I want to do is to try to calculate for the probability for each of them to be accepting a box. Let's start with Mr. Lu. So for part B over here, I'm going to try to calculate for the probability that Mr. Lu accepts a box. Okay, and for Mr. Lu to accept a box, according to the question, out of these 6 pens that are selected from that are obtained from the box, there must be either no 40 pens, which means that all the pens are going to be working. And for a pen to be working, the probability is P. So all the pens are working, it will be P to the power of 6, or 1 is going to be 40, which means that 5 are going to be working. We can either apply the binomial distribution, because this really exactly follows a binomial distribution, or we can just jump directly into using the formula for the binomial distribution, which will be out of the 6 pens that are chosen, we want 5 of them to be working. So the probability of a pen working is going to be P, so it will be P to the power of 5. And then that last pen will be not working. It is going to be this. This, if I were to just press in my calculator 6 choose 5, which is going to be equal to 6. Expanding this, simplifying this, I'm going to be getting a 6p to the power of 5 minus 5p to the power of 6. This is when Mr. Lu accepts a box. We are going to do likewise for Mrs. Ming. So the probability that Mrs. Ming accepts a box. And this will be, let's read the question. Mrs. Ming will be selecting 3 pens from the box. It will be accepted if, again, there's no 40 pen in her sample. So all the 3 are going to be accepted. So it's going to be P to the power of 3. Or if there were to be 140 pen in her sample, she's going to take another sample, the second sample, and this second sample, which will be also of 3 pens, if there were to be still no, like totally no 40 pens in the second sample, then she'll be accepting the box. So this will be the case where there is 1 pen that is 40 in the 3 samples, so 2 are working. So out of 3, we will choose 2 to be working, P to the power of 2, then 1 minus P. And then she will continue with the second sample, and this time for the second sample, all 3 must be working. So this will be P to the power of 3. And again, if you were to press into the calculator, 3 choose 2, which is 3, expanding this and simplifying this, you will be getting a P to the power of 3 plus 3P to the power of 5 minus 3P to the power of 6, which will represent the probability that Mrs. Ming accepts a box. And in order for me to try to show algebraically that this probability is greater than this probability, what I'm going to try to do is to find the difference between them. Specifically, I think I'm going to try to take this probability minus away this, the probability that Mr. Lu accepts a box. And my objective is to try to prove that this is going to lead me to a positive value. So because if it is positive, then the proportion of Mrs. Ming accepting the boxes will be greater than the proportion for Mr. Lu to be accepting the boxes. So let's try to prove that this is positive, which will be requiring me to take this P to the power of 3 plus 3P to the power of 5 minus 3P to the power of 6 minus away this 6P to the power of 5 minus 5P to the power of 6. Simplifying this, I will be getting a P to the power of 3 minus 3P to the power of 5 plus 2P to the power of 6. Let me try to factorize this. If I were to factorize out 3, I'll get 1 minus 3P squared plus 2P to the power of 3. I will probably use my calculator to help me to factorize this further. And that will be giving me a P minus 1 squared, then 2P plus 1. And if I were to be analyzing the expression that I have here, we know that this is going to be bigger than 0 because P is the probability. It has to be between 0 to 1. We know that this is also going to be bigger than 0 because P minus 1 square, it is always going to be bigger than 1. And since P is bigger than 0, 2 times P plus 1 is also bigger than 0. So based on this, we can then conclude that this entire expression here is bigger than 0. And if this entire expression here is bigger than 0, we can subsequently also conclude that Mrs. Ming is going to be accepting a greater proportion of boxes than Mr. Lu.